Welcome to True Projects. In this video, we are going to explain about the project entitled as Retinal Image Analysis for Heart Disease Prediction, a deep learning approach. So before getting into the video, let me give you the brief description about the project. This title highlights the use of retinal fundus images to access the risk of heart disease by analyzing vascular and structural patterns in the eye. Since the retina reflects schematic blood vessel health, deep learning models can automatically learn meaningful features linked to cardiovascular conditions. The approach leverages convolutional neural networks to extract complex retinal features and predict heart disease risk in an non invasive and efficient manner. Coming to the abstract describes a project focused on addressing the global challenge posed by cardiovascular diseases by introducing an early, accurate, and non invasive risk prediction method. It explains that recent advancements in medical imaging and artificial intelligence have made it possible to analyze retinal fundus images as indicators of cardiovascular health. Since the retina microvascular structure closely reflects the condition of the body's overall vascular system, the project proposes using deep learning techniques, particularly convolutional neural networks, to automatically learn and extract complex patterns from retinal images they may be associated with heart disease risk. By classifying individuals based on these learned features, the system aims to support early detection and preventive care. Overall, the approach offers a cost effective, scalable, and efficient screening solution that can enhance traditional cardiovascular risk assessment methods and improve clinical decision making. Coming to the existing system for heart disease risk prediction is largely based on traditional clinical assessments and laboratory investigations, including factors such as age, blood pressure, cholesterol levels, blood glucose, lifestyle habits, and, in some cases, invasive diagnostic procedures. While these methods are clinically established, they are often time consuming, costly, and dependent on specialized medical infrastructure, making them less accessible in low resource or remote settings. Many current systems that uses machine learning rely on manually engineered features and predefined rules, which restrict their ability to capture complex patterns and reduce adaptability to diverse patient data. Furthermore, although retinal image analysis is widely applied for diagnosing eye related conditions like diabetic retinopathy, it is rarely integrated into cardiovascular risk assessment frameworks. This separation limits the potential use of retinal biomarkers for systematic health evaluation, resulting in less comprehensive and less effective heart disease prediction systems. Coming to the proposed system or base paper work, the proposed system presents an advanced deep learning based approach for predicting heart disease risk using retinal fundus images in a completely non invasive manner. It employs a convolutional neural network trained on labeled retinal image datasets to automatically identify and learn meaningful features related to cardiovascular health, such as blood vessels width, vessels tortuosity, branching patterns, and microvascular abnormalities. Unlike traditional methods, the system removes the need of manual feature extraction and invasive clinical tests, thereby improving efficiency and reducing dependency on extensive medical procedures. The framework integrates image processing, automated feature extraction, and classification into a single end to end model, enhancing prediction accuracy and robustness. Overall, the proposed system offers a scalable, cost effective, and easily accessible solution for early heart disease risk screening, supporting timely diagnosis, preventive care, and improved patient outcomes. Coming to the dataset, the IPACS dataset is large scale and widely used medical imaging dataset consisting of high resolution retinal fundus images collected during real world diabetic retinopathy screening programs. The images were captured using different types of fundus cameras under variant clinical conditions, resulting in significant diversity in image quality, illumination, and resolution. Each retinal image is carefully annotated by certified ophthalmologist and assigned a diabetic retinopathy severity label range from 0 to 4, where 0 represents no signs of DR and 4 indicates diabetic retinopathy. The publicly available portion of the dataset contains approximately 35,000 labeled trained images along with a large number of test images, making it a standard benchmark for retinal image analysis and deep learning research. Due to its real world nature, the dataset exhibits class imbalance with a higher proportion of normal cases compared to severe DR cases. In this project, the IPACS dataset is utilized to extract clinically relevant retinal features that reflects microvascular health, which are then leveraged to support heart disease risk prediction, highlighting the relationship between retinal biomarkers and somatic cardiovascular conditions. Coming to the novelty or extinction or enhancement or improvement. In the base paper, the author utilized EfficientNet B3 as a feature extractor combined with custom CNN layers for classification, achieving better performance when compared with other baseline deep learning models. The base work also incorporated explainable AI techniques, specifically GradCam, to generate heat maps that highlights the important regions of retinal images influencing the model's prediction, thereby improving interpretability and trust. As an extension to this work, the YOLO family model was applied to detect and localize abnormalities in retinal images, enabling precise identification of affected regions. This extension enhances the system by moving beyond classification to include real time object detection of pathological features within the retina. Additionally, a Flask based web application was developed to provide a user friendly interface allowing users to upload retinal images and obtain predictions using the trained model. The integration of detection models and a web based UI improves system accessibility, usability, and practical deployment for real world screening applications. Coming to the flow of the work, first we need to import the packages. This initial module involves importing all the required Python libraries and frameworks needed of the project. This includes deep learning libraries such as PyTorch, Torch Vision for model deployment, OpenCV and Pillow for image handling, NumPy and Pandas for data manipulation, scikit-learn for evaluation metrics, YOLO frameworks for object detection, and Flask for deploying the web interface. This module ensures that the environmental is properly set up before the data pre-processing and model training begins. Next, dataset preparation. The IPACS dataset is collected from Kaggle and organized for further process. Retinal fundus images and their corresponding diagnostic labels are prepared for classification tasks. Additionally, clinical features are derived based on IPACS diagnostic labels and disease severity, which are later used for heart risk prediction. The dataset is structured to support both classification and detection tasks, forming the foundation for the entire system. Next, pre-processing. This module prepares the data for effective training of deep learning modules and is divided into two branches. One classification pre-processing and then detection pre-processing. First, for classification, image data augmentation techniques are applied to improve model generalization. Images are resized to 299 into 299 format, randomly flipped horizontally, rotated, and converted into tensor format using torch vision transformers. The steps helps the model handling variations in image orientation, scale, and lightening. Coming to the detection pre-processing, for detection, multiple datasets are merged into a single dataset to improve detection performance. Bounding box annotations are standardized and the data.yaml file is created for YOLO models, defining dataset paths and class names. This formatting is essential for training YOLO-based object detection model. Next, maintain parallel datasets. In this module, two parallel datasets are in pipeline. The classification pipeline uses retinal images paired with class labels, while the YOLO detection pipeline uses retinal images with bounding box annotations. Keeping this dataset separately ensures that both classification and detection models receive data in the correct format without interference. Next, model training. This core module handles model training and performance assessment. Here we have classification model training, YOLO based model training, and model evaluation. In classification, a five-fold cross-validation strategy is used to ensure robustness and reduce overfitting. Multiple baseline models such as DESNet 50, VGG16, and a base CNN are trained for comparison. The proposed model uses EfficientNet V2 as a feature extractor combined with CNN 1D layers, offering improved feature representation and classification accuracy. And for YOLO based detection model training, as an extension, multiple YOLO versions are trained to detect the localized retinal abnormalities. Each YOLO model learns both the location of pathological regions and their corresponding class labels. Next, evaluation. Classification models are evaluated using the metrics such as accuracy, precision, recall, F1 score, confusion metrics, sensitivity, specificity, and ROC curves. YOLO models are evaluated using mean average precision, and recall. And different YOLO versions are compared to identify the best performing detection model. Next, we have interference pipeline. This final module focuses on real time predictions and system deployment. Users upload retinal images along with clinical features through a Flask based web application. The backend first runs the YOLO detection model to identify and localize abnormalities with confidence score. The detected image and extracted features are then passed to the fusion classification model, which predicts the heart disease risk class. The results are displayed on the web interface, showing the image with bounding boxes, predicted class, and confidence score, providing an intuitive and accessible screening tool. The algorithms used in the project are baseline models, ResNet 50, VGG16, CNN based model. And for proposed model, we have used EfficientNet V2, feature engineering with CNN 1D. Extension YOLO based detection models, we have used YOLO V5, YOLO V8, YOLO V9, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework, Anaconda, primary language, Python, front-end framework, Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project first, we need to open the code folder which contains project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Model files. In these files, the information related to the algorithms will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. so that the home page of the project should now be displayed in the Chrome. This is a front end built using Flask framework. In this page, we have home button and get started button. Firstly, click on get started button so that the create account form will be open where you need to enter the details for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on sign up so that all the given details are stored in signup.db and sign in form will be open where you need to access the application with the help of username and password. Then click on sign in so that the prediction page has been displayed. In this page, we have home button, prediction button, data visualization button, notebooks button, and logout button. Firstly, click on prediction button so that the upload funders image form and clinical parameters form will be open. In the left side, we need to enter the image, like we need to upload the funders image, and on the right side, we need to give the parameters of the patient clinical data. Firstly, let us choose the fundus image. The image has been successfully loaded. Now, let us give the parameters. Systolic BP, the value will be. Diastolic BP value will be. The cholesterol value will be. BMI value will be. HbA1c value will be. Diabetes value will be. Smoking value will be. And age. Now, let us click on predict disease risk. So the given input like image and the parameters are pre-processed and the output is displayed as high risk and the final probability is 1.0. Overall risk probability is 100% based on the retinal image analysis and the clinical parameters. This is a euro detection result and this is a GradCam visualization image. And we have the clinical parameters are given here clearly what we have entered. And we also have the recommendations and safety precautions like immediate actions, lifestyle modifications, medical management, and warning signs to watch. Now click on new prediction. So again, the upload funders image form and the parameters form will be open where you need to upload the funders image. The image has been successfully uploaded. Now let us give the parameters. Systolic BP value will be, diastolic BP value will be, cholesterol value will be, BMI value will be, HbA1c value will be, diabetes value will be, smoking value will be, the age is of. Now click on predict disease risk so that the given input and the parameters are pre-processed and the output is displayed as low risk. The final probability is 0.0232% and the overall risk probability for the given retinal image analysis and clinical parameters are 2.32%. And we also have the euro detection result where it is very low and the GradCam visualization, and we have the clinical parameters which we have entered clearly, and then recommendations and safety precautions are given like good news, maintain healthy habits, regular monitoring, prevent measures, and also stay informed. Now click on data visualization button so that the graphical representation of the projects will be displayed. Now let us check one by one. First, we have confusion matrix graph. The confusion matrix shows that the model performs extremely well in classifying heart disease risk. Out of all samples, 599 low risk cases and 600 high risk cases are correctly predicted, indicating very high accuracy. Only one high risk case is misclassified as low risk, and there are no false high risk predictions for low risk patients. Overall, this graph reflects excellent classification performance with minimal error and strong reliability. Next, we have ROC curve graph. The ROC curve illustrates the model's ability to distinguish between low risk and high risk heart disease cases. The curve closely follows the top left boundary, indicating an excellent trade-off between true positive rate and false positive rate. An AUC value of 100 signifies perfect classification performance with no overlap between classes. This confirms the model's high reliability and discriminative power. Next, we have accuracy by model graph. The bar chart compares the classification accuracy of different deep learning models using in the project. The baseline CNN shows the lowest performance while VGG16 and ResNet15 achieve significantly higher accuracy. The proposed model outperforms all baseline models, achieving near perfect accuracy. This demonstrates the effectiveness of the proposed architecture for heart disease risk prediction using retinal images. Next, we have F1 score matrix analysis graph. The graph presents the F1 score comparison of different models, reflecting the balance between precision and recall. The baseline CNN shows the lowest F1 score, indicating weaker and less stability predictions. Both VGG16 and ResNet50 achieves higher F1 scores, while the proposed model attains the highest value, close to 1.0%. This confirms that the proposed model provides the most reliable and consistent classification performance. And next we have recall metrics graph. The graph compares the recall performance of different models, indicating how well each model identifies positive cases. The baseline CNN shows lower recall, meaning it misses more true positive cases. VGG16 and ResNet50 demonstrate strong recall values, while the proposed model achieves perfect recall. This indicates that the proposed model is most effective in correctly identifying all high-risk heart disease cases. Next, we have precision metrics analysis graph. The bar chart compares the precision of four machine learning models. The baseline CNN has the lowest precision, around 0.68%, indicating more false positives. VGG16 and ResNet perform significantly better, both close to 0.97 to 0.98 precision. The proposed model achieves the highest precision at 1.0%, showing the most accurate predictions among all models. Next, we have error by model graph. The graph shows the error rate of different machine learning models. The baseline CNN has the highest error, indicating weaker performance. VGG16 and ResNet50 significantly reduce the error, showing improved accuracy. The proposed model has nearly zero error, demonstrating the best overall performance. Next, we have sensitivity by model graph. The bar chart compares the sensitivity of four machine learning models. The baseline CNN shows the lowest sensitivity, while VGG16 and ResNet15 perform noticeably better. The proposed model achieves the highest sensitivity, reaching nearly perfect detection. Overall, the graph shows a clear improvement in sensitivity with more advanced models. Next, we have specificity by model graph. The bar chart illustrates the specificity of different machine learning models. The baseline CNN has significantly lower specificity, indicating more false positives. VGG16 and ResNet50 shows high and similar specificity values. The proposed model achieves the highest specificity, demonstrating the best ability to correctly identify negative cases. Next, we have YOLO MAP by model graph. The bar chart compares the MAP performance of different YOLO versions. Next, we have YOLO recall graph. The bar chart compares the recall performance of different YOLO model versions. YOLO V5 achieves the highest recall, indicating better detection for relevant objects. YOLO V8 and YOLO V11 shows comparably performance, while YOLO V9 has the lowest recall. Overall, the results highlight variations in recall across different YOLO architectures. Next, we have YOLO precision by model graph. The graph compares precision scores of different YOLO models. YOLO V8 shows the highest precision, indicating the most accurate positive predictions. YOLO V5, YOLO V9, and YOLO V11 have very similar precision values, slightly below YOLO V8. Overall, all models demonstrate strong and comparable precision performance. Then click on Logout. So finally, this project demonstrates that retinal image analysis using deep learning is a promising, non-invasive approach for prediction heart disease risk. By leveraging CNN-based models and retinal biomarkers, the system effectively captures microvascular patterns associated with cardiovascular health. The integration of classification, detection, and explainable AI enhances both accuracy and interpretability. Overall, the proposed approach offers a scalable and cost-effective solution for early heart disease screening and preventing healthcare. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.